Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish.
Despite humanity's extensive exploration of the solar system, new discoveries continue to amaze us. For years, we believed we had identified all the planets until we were proven wrong. But what about the Voyager probes? Just how far have they traveled beyond our solar system? Even scientists are astonished by the groundbreaking insights these spacecraft have provided. One of the most intriguing revelations is that our entire solar system, including the distant Oort cloud nearly a light-year away, is enclosed within a massive cosmic bubble. This bubble stretches an astonishing 1,000 light-years across, with the Sun positioned near its center. But what happened when the Voyager probes crossed the boundary of our solar system? Could we actually be trapped inside this immense space bubble? And how does this discovery transform our understanding of the solar system structure? Let's explore the answers. On September 5, 1977, NASA's Voyager 1 spacecraft launched from Cape Canaveral, Florida, aboard a Titan Centaur rocket just weeks after Voyager 2's launch on August 20th. Originally designed for a 5-year mission to study the outer planets, these resilient probes have surpassed all expectations, continuing to send data back to Earth more than 44 years later as they venture into interstellar space. The Voyager missions capitalized on a rare planetary alignment that occurs once every 107 years, allowing the spacecraft to perform gravitational slingshots from one planet to another, conserving their limited fuel. Despite launching second, Voyager 1 was the first to reach Jupiter and Saturn, focusing on these planets, while Voyager 2 explored Jupiter, Saturn, Uranus, and Neptune. Over a decade, the data transmitted by the Voyagers have profoundly shaped our understanding of the outer solar system, earning their place in textbooks and media alike. As a unique touch, each spacecraft carries a golden record, a time capsule of Earth sounds and music intended to communicate with potential extraterrestrial life. As of January 2024, Voyager 1 is around 14.9 billion miles from Earth, 158 times the distance between our planet and the Sun, making it the most distant human-made object in space. Voyager 2 reached a significant milestone in November 2018, becoming the second spacecraft to enter interstellar space after Voyager 1's historic breakthrough in August 2012. Voyager 1's exit from the heliosphere, a vast bubble of charged particles shaped by the Sun, was confirmed when its plasma wave instrument detected a powerful solar eruption between April 9th and May 22nd, 2013. This eruption caused nearby electrons to vibrate, leading researchers to discover that electron density outside the heliosphere was much higher than within it. The findings highlighted a striking contrast. While interstellar space is denser than regions near the Sun, the outer boundary of the heliosphere is far less dense than areas closer to Earth. By analyzing this data, scientists pinpointed Voyager 1's official entry into interstellar space to August 25, 2012, using electron oscillation measurements and observations of charged solar particles. Voyager 2 followed suit, crossing into interstellar space 6 years later, confirming the profound scientific significance of these twin spacecraft. The data from the Voyager spacecraft reveal many similarities, such as the overall density of particles encountered in interstellar space. However, their journeys revealed notable differences, sparking new questions about the Sun's trajectory through the galaxy. Outer space continues to defy our expectations, and Voyager 2's observations as it crossed the Heliopause provide even more insight into this vast and mysterious frontier. The boundary between the heliosphere and interstellar space is revealing some of the solar system's deepest mysteries. To fully appreciate Voyager 2's groundbreaking discoveries, it's crucial to first understand the Sun's dynamic nature. Contrary to its serene appearance, the Sun is a massive nuclear reactor blazing through the galaxy at roughly 450,000 kilometers per hour. Its surface is a complex network of magnetic fields that generate a constant stream of electrically charged particles, known as the solar wind. This solar wind expands outward in all directions, carrying the sun's magnetic field across immense distances. Eventually, it collides with the interstellar medium, a region filled with remnants of ancient stellar explosions. Like oil and water, the solar wind and interstellar medium resist blending, forming a distinct boundary known as the heliosphere. This vast bubble, powered by the solar wind, extends roughly 11 billion miles from the Sun, encapsulating the Sun, all 8 planets, and a significant portion of the solar system's outer regions. Strange, isn't it? But it's the kind of strangeness that works in our favor. The heliosphere acts as a protective shield, guarding everything inside, including us, from the galaxy's most dangerous radiation. Without it, life as we know it would be exposed to potentially catastrophic hazards. The outer edge of the heliosphere, called the Heliopause, marks the beginning of interstellar space. Understanding this boundary has profound implications for comprehending the Sun's movement through the galaxy, as well as the conditions around other stars scattered across the cosmos. Scientists are especially intrigued by the interactions at this threshold, how the solar wind and interstellar media mix, the extent of material exchange across the boundary, and the dynamics of this cosmic collision. When Voyager 1 crossed the Heliopause in 2012, it offered the first direct glimpse into this enigmatic region. However, analyzing its data proved challenging. Scientists found that the interstellar magnetic field was 2 to 3 times stronger than anticipated, indicating that interstellar particles exert up to 10 times more pressure on the heliosphere than previously estimated. Yet, Voyager 1's findings were incomplete due to the failure of its plasma instrument in 1980, leaving gaps in the data. In 2018, Voyager 2 provided a crucial breakthrough. With its plasma instrument fully operational, scientists obtained a clearer picture of the Heliopause. As the spacecraft neared the boundary, they observed that the surrounding plasma slowed, heated up, and became denser, revealing key details about this critical interface. Beyond the Heliopause, the interstellar medium was found to be far hotter than expected, with temperatures reaching at least 54,000 degrees Fahrenheit. However, because the plasma is extremely thin and diffuse, the overall temperature around the Voyager probes remains very low. Voyager 2 also confirmed that the Heliopause is a porous boundary, allowing particles to move in both directions. For example, Voyager 1 encountered 10 streams of interstellar particles that penetrated the Heliopause, resembling tree roots breaking through rock before fully crossing the boundary. Meanwhile, Voyager 2 detected a subtle flow of low-energy particles, extending more than 100 million kilometers beyond the Heliopause. As Voyager 1 approached the boundary, the outgoing solar wind slowed dramatically, creating an eerie limbo-like state. In contrast, Voyager 2 observed a unique transitional layer in the solar wind, similar in width to the stationary zone observed by Voyager 1. This disparity underscores the complexity of the heliosphere and highlights the need for more data to unravel its mysteries. The solar system appears to be as adaptable as a chameleon, with puzzles that demand a broader understanding of the heliosphere. Voyager 1 exited the heliosphere at its leading edge, encountering the interstellar medium, while Voyager 2 departed through the left flank. However, the heliosphere's wake remains unexplored, leaving its overall shape uncertain. It could be spherical due to interstellar medium pressure, or it might have a comet-like tail, or even a glass-like form. Unfortunately, current spacecraft won't provide definitive answers. NASA's New Horizons, though fast, will lose power in the 2030s, still over 1 billion miles short of the Heliopause. This limitation has fueled calls for a follow-up interstellar mission, a multi-generational effort to explore the outermost reaches of the solar system and beyond. With data from only 2 points, our understanding of the heliosphere's structure remains incomplete, making additional data crucial. Beyond the Heliopause, Voyager 1 made another intriguing discovery: a persistent hum. Upon entering interstellar space, its plasma wave instrument detected oscillations in the interstellar gas caused by solar activity. However, between these bursts, it also picked up a faint, continuous signal. In 1 billion years, the Voyager probes will have ventured far beyond the boundaries of our solar system, drifting through the vast expanse of interstellar space. By then, Voyager 1 and 2 will be barely recognizable, their instruments long silent as their power sources deplete. Yet, they will persist in their journey, traversing the galaxy on a course that will eventually carry them 50,000 light-years from the Sun, across the Milky Way. Voyager 1 is currently en route to a distant star known as AC plus 793888, while Voyager 2 is headed toward Ross 248, a star in the Andromeda constellation. However, it will take tens of thousands of years before these probes come anywhere near their target stars. As they continue their odyssey, the most thrilling discovery in the next 3 to 5 years may be something beyond our wildest imagination.